Welcome to this primer on posets. In this lecture, we'll define what is a poset and give some examples. We will not be proving any results and only be discussing the definitions. But since the notion of posets is very fundamental to all mathematics, it is a good idea to be aware of them. And the only prerequisite is the idea of relations. We have a few videos on these in the playlist named Kickstart. You can refer to those videos or you can just Google around. It is not a difficult concept. And to follow those lectures, those videos on relations, you further need to know about sets, which are also available in the same playlist. So this playlist is supposed to be something that, as the name suggests, get you started with higher mathematics. All right, so with that, let us begin. So first, before we define a poset formally, first let us look at a basic example. So a poset is trying to give the notion of order on a given set, and we already know an example of order, namely on the set of integers. So the set of integers are these, and we already know how to compare things here, right? We know what it means to say 2 less than equal to 3. So we are already familiar with a notion of ordering on integers. Let us just note a few properties that this symbol enjoys. So the first property is n less than equal to n for all n. Right? That is there. Second is if two integers are both less than equal to the other, then they are equal. And lastly, if m is less than equal to n, and unfortunately O is a very bad symbol, so I will have to resort to P. So if m is less than equal to n and n is less than equal to P, then so these three properties are, they hold. There is also an extra property. So if m and n are integers, then either this or that, or both, of course. Both happen if and only if m and n are equal. So these four properties hold, and in the notion of a poset, we will be retaining these three properties and relinquish the last one. So now we will make this precise. So what is a poset? Before we answer that, first we will note what is a partial order. So let P be a non-empty set. A partial order on P is a relation which we denote by this symbol. And this symbol, of course, we just saw in the context of integers, but we are now abstracting that the properties out. So now do not associate any meaning to it apart from what we are going to discuss. Okay, so a partial order on P is a relation which we denote by this symbol such that three properties are satisfied. First is reflexivity, which says that X is related to itself for all elements of the set P. Second is antisymmetry. If X and Y in P are such that right, this is what we saw in the context of integers also. If you have two elements in P such that they are both related to each other in, if X is related to Y and Y is related to X in this way, then they are actually equal. And the last property is transitivity. If X, Y, Z are in P such that X is less than equal to Y and Y is less than equal to Z, then right. So we have abstracted out the three properties that we saw for integers, and any relation satisfying these three properties is called a partial order on P. Alright, now a partially ordered set partially ordered set or a poset. So P, O and set. A poset is a pair where P the non-empty set and this is a partial order on P. Alright, so this is a very abstract definition. Right now it may not even be making much sense as to what the hell is going on. But with any abstract definition, the way to understand it is via examples. Alright, so let us look at examples. So we have the set of first n natural numbers. N is some fixed natural number. So there is a usual ordering on it, just the usual way of comparing natural numbers. And once you equip this with that ordering, it becomes a poset. So I should also mention here, we have defined a partially ordered set as a pair, but we may use phrases like let P be a poset. So when we say something like this, we really mean that we have a relation on P with those three properties, but the symbol for the relation is, this one. So one is not obliged to use this particular symbol, but this kind of abuse of language is rampant in all mathematics, and it is a good thing that it is. Every time making these pairs is not convenient. So when we say let P be a poset, we are implicitly suppressing the symbol that we have, which is actually the partial order. Alright, so when we say this becomes a partial order when equipped with the usual order, we really mean the pair, this comma the relation, the usual ordering relation becomes a poset. Alright, so that's just a remark on the language that we use. So this I don't want to say anything about, but now for the interesting example of Boolean posets. Alright, so let X be some non-empty set. And let P be equal to the power set of X. Okay. So P right now is just a non-empty set. Now what we do is define a relation on P as if A and B are in P, which is to say that A and B are subsets of the set X, where empty set is also allowed. A could be the empty set, and that's perfectly okay. If A and B are in P, then A less than equal to B if and only if A is contained in B. So this is our definition of the partial order on P. So of course, when we call it a partial order, we have to actually verify the three properties. So reflexivity is very simple, because if A is any subset of P, then A is obviously contained in itself, and hence A less than equal to A holds. For antisymmetry, if A and B are two subsets of X, and A contained in B and B contained in A, then A is equal to B. So therefore antisymmetry holds. And lastly, if A contained in B and B contained in C, then A contained in C. So this proves transitivity. So basically the inclusion relation that we have on the set of all the subsets of X is our partial order. So that is a partial order, but of course the fourth property that we had in integers is not satisfied. It is not true that whenever you are given two subsets of X, one is contained in the other. That is clearly false. All right, so this is for a general X. Let us look at when X is the simple set A comma B. So this one is when X is equal to A comma B, just the two element set. What are all the subsets? The empty set, the singletons A and B, and the full set X. And the empty set is smaller than that because it is contained here. It is also contained here. This guy is contained there, and this guy is also contained there. So we have just drawn these lines to depict containments. So this is a very nice diagram denoting or capturing the poset, the power set of X. This is X and this is the power set of X. Similarly, if X is the three element set, then there are 8 subsets of X. Empty set, the singletons, which somehow I have forgotten to yeah, I have mislabeled a few things. So these are the singletons. Just give me 1 second. Yeah. So these are the 3 singletons, and then the doubletons, meaning the 2 element subsets. So of course A is contained here and A is contained there. C is contained here and C is contained there, and B is contained here, B is contained there. And then we have the full thing. So there are 8 things in the power set of X. They are kind of layered, and this looks like a very nice thing. So that's the example of the Boolean posets. And now let us look at the division poset. So let n be some positive integer, and let dn be this set. And what is the poset structure, or what is the partial order? So define a relation on dn as if A and B are in dn, then A less than equal to B if and only if A divides B. So that's the definition of this relation, and one can easily check that this is partial order, meaning it is reflexive, antisymmetric, and transitive. So that's a very nice partial order on dn, and therefore we get a poset. It's a poset. And of course this poset structure is different from the usual ordering. In the usual ordering, it is very simple to visualize, 1, 2, 3 up to n, but here not every 2 elements are comparable, meaning the fourth property that we saw in the integers is not true anymore. So this is more interesting or more exotic than your usual ordering. All right, lastly, let us look at this example. This is an abstract example. So suppose we are given 2 posets. Now this may be confusing because we are using the same symbol for the relation on P and Q. This is very common. This is a very common practice, although not I mean, this is in some sense abuse of notations, but that this is okay. We do this frequently. We just need to be aware as to which one is being used where. All right, so let P and Q be posets. Then define a relation which we again denote like this on P cross Q. This is the Cartesian product of P and Q as A comma X less than equal to B comma Y. So this is an element of P cross Q and that is an element of P cross Q, which means that A and B are in P and X and Y are in Q. If and only if, just give me 1 second. If and only if A is less than equal to B and X is less than equal to Y. So when we write this symbol, we are using this one because A and B are elements of P, and when we are writing this symbol, we are using that one because X and Y are elements of Q. So the way to compare two elements in P cross Q is just you compare them coordinate-wise, so to say. And then you can check that this gives a partial order on P cross Q, and this is called the product of two posets. So you can build new posets out of old posets just by taking products. Alright, so this is all that I wanted to say in this lecture. As usual, like, comment, share, subscribe, and I will see you next time.